In the last two videos, we talked about how to compute the AND function using a simple neural network with one neuron. In the first video, which you can find in the comments section, we guessed the weights. In the second video, we showed how to find the weights mathematically by looking at the constraints. In this video, we're going to expand these ideas a little bit more to introduce a concept called backpropagation. So, restating the problem, our task is still to build a simple neural network to calculate the logical AND function. There are two binary inputs and one binary output. This is not a complex function, so we actually don't need a neural network to compute it. However, this is a great example to demonstrate how neural networks work. So we looked at two approaches to finding the weights. We need to compute the function h theta x equals sine theta 0 plus theta 1 times x1 plus theta 2 times x2, where we have one neuron and three inputs. One is the bias input 1, and then the two inputs x1 and x2, which are binary inputs. We are trying to figure out how to find the weights theta underscore 0 theta 1 and theta 2 to compute the AND function. In approach 1, we just guessed the weights to be minus 20, 10, and 10, and then we plugged these into h theta x for each of the inputs x1 and x2. There are 4 of those. We came up with a number, and for each number, the predicted input class should be 1 or 0. After you apply the sigmoid function, if the number is more than 0.5 comma, we're going to predict this to be class 1, otherwise class 0. In the second approach, we mathematically analyze the properties of the weights. We tried to figure out what the constraints on theta underscore 0, theta underscore 1, and theta underscore 2 are under the conditions that we want to get these outputs. We found that many combinations of thetas can satisfy these constraints, as in approach 2. You can watch the previous videos to see more details. So in this video, we will try to determine the weights using backpropagation. We have 4 pairs of inputs and the outputs are given as 0 or 1. We'll take a different approach than guessing weights or mathematical analysis. The method called backpropagation is more scalable and practical. So what's backpropagation? Mostly you run the network forward on a training example to see what output it produces. Then you compare the output to the desired output to see how far off you are. For example, if you predicted 0 and actual output is 1, then we are off. We need to increase the value of predicted by going backwards and gradually adjusting the weights. In the forward propagation, we take the inputs and multiply by weights. For example, we can get the input 1, 0, 0, where 1 is the bias and x1 is 0 and x2 is 0, and say weights minus 10, 20, 20, and we produce an output theta 0 times 1 plus theta 1 times x1 plus theta 2 times x2. Then, if the output is greater or equal to 0, we call it 1 and otherwise 0. This is actually different from sigmoid function we looked at. This activation function is called ReLU function. So let's train this neural network. We have 4 samples including the bias input. We can see the 4 samples here, and we also see the desired y, or the label. We want the h theta x to produce the same output, and only when x1 equals 1 and x2 equals 1 should the perceptron. Let's take the initial weights to be 1, 1, 1. By the way, we can start with any weights, and we will iteratively find the weights that we need. So here's our trial and error update rule. First, we compute the predicted value y hat using the h theta x function. Then we compare with the observed value y. For example, if y is 1 and we predicted y hat to be 0, then the prediction is low. So we need to increase the weights to adjust for the error. So we add x to theta. On the other hand, if observed y is 0 and we predicted 1, then the prediction is high and we need to decrease the weights to adjust for the error. So we subtract x from theta. If the observed and predicted agree, both 1 or both 0, then there is no adjustment necessary. Let's go through an example to see how this works. Let's start with the initial theta as 1, 1, 1. We'll look at the first input sample 1, 0, 0. For sample 1, 0, 0, we are supposed to get the output y equals 0. We compute theta 0 plus theta 1 times x1 plus theta 2 times x2, and then we get 1. Since y hat, which is 1, is substantially greater than the expected output, we are going to decrease each of the weights by the difference minus 1. We do the same thing with theta 1 and theta 2. At the end of the first run with all 4 samples, we have a new set of weights, minus 1, 1, and 1. This is called the epoch 1, that is going through the data set once. So now we will perform epoch 2 starting with our new weights -1, 1 and 1. The updating weights rules are the same. If predicted is higher than observed, we proportionally reduce all the weights. If predicted is lower than observed, we increase all the weights proportionately. If they are the same, we do not adjust the weights. At the end of epoch 2, we now have a new set of weights -1, 2 and 1. We run the third epoch using these weights and receive new weights -2, 2 and 1. Continuing the same process for epoch 4 and epoch 5, which we recommend you do, we get the final weights -3, 2, and 1. So how do we know when to stop the epochs? When the weights do not change, that is observed and predicted are the same, we can terminate the process. This is how we got these final weights -3, 2, and 1. The process of finding the weights is a bit of trial and error. We did not use explicit derivatives or sigmoid function. We kept things fairly simple. The final weights correctly implemented the AND function. The back propagation algorithm we presented in this video is based on a simple adjustment. In the next video, we will discuss a widely used gradient descent method, which is commonly used in machine learning algorithms. However, this requires some basic understanding of calculus. It is truly a great algorithm. If you're interested in questions related to this video, please visit the Qubits course given in the comments section. Until next time,